I had a look at the previous session, the results, and I was quite impressed. It seems that the inbuilt microphone in the camcorder is highly forward directed. I didn't hear any background traffic noise, and it's certainly there, but I didn't hear anything, so that's great. And I noticed the lighting, it seems to make this whiteboard look a little bit blue board unless you raise the intensity of the lighting. So I think I'll keep doing this for a while. So far it's nearly 5 a.m. I'm a night person. I'm retired, right? So I just do what I like, and I prefer working at night because the internet speed is so much faster at night when China sleeps, so it's a major advantage. Plus, just by nature, I guess. Right, we'll push on with more examples of homomorphisms. The chapter has 8 of them, so quite a few. So, talk now about a particular kind of homomorphism that's called a trivial homomorphism, and it's trivial in the following sense. So imagine, like, here you have your two groups, G and H, and imagine every element of G gets mapped by F into the unit of H, right? All of them, just every element here gets mapped to E. That mapping, that function, that F, is labelled trivial homomorphism, right? For fairly obvious reasons, right? It all goes to just one element of H, the unit, H's unit, right? So now we can show pretty quickly that it is a homomorphism. You know, the usual thing, f of x, f of y equals f of xy, right? The usual trick. Well, since everything maps to E, so f of x will map to E, that's E of H, right? The unit of H. So this will map to E, and f of y will map to E, so you get E twice, which is just E. And xy, just two elements in here, so the result xy will be some element of G, right? Because it's closed, it's a group, G is a group, right? So whatever element this is, it too, because everything gets mapped to E, so this too will get mapped to E, right? And therefore you've got fx, fy equals fxy, right? So this trivial homomorphism, well, this mapping is a homomorphism, right? There's the proof that it is a homomorphism. And because it's a special case where everything gets mapped to just the unit, this homomorphism is called a trivial homomorphism, right? Now, interestingly, sometimes when you try to map one group to another group, sometimes the only homomorphism that exists between those two groups is the trivial homomorphism. So here's a case here where, yeah, that's showing that's true. That the only homomorphism that exists between these two groups, Z3 and Z2, the only one that does exist is this trivial homomorphism, and we'll prove it here and here, that there can be no other homomorphism other than this one. There is no second one. It's only of this kind. For certain cases, you know, for certain pairs of groups. So okay, so let's try to find homomorphisms between this group and this group, right? Now it's Z3 and Z2, and I'm going to switch back and forth between notations, like the long-handed way and the shorthand way. Because remember, these are sets, well, groups, but they're sets of residue classes. And remember, I've said this quite a few times now, but residue classes tend to behave like integers. So this here, that is Z3, right? It's the residue class 0, mod 3, residue class 1, mod 3, residue class 2, mod 3. those three elements are the elements of Z3. Right? And similarly for Z2, residue class 0 mod 2, residue class 1 mod 2. Right? So you're mapping this group into this group. So you're mapping this group into this group. That's the long-handed way, the residue class notation, right? This way. Now the shorthand way, we forget about the square brackets, we forget about the mods, we just say 1, 2, 3, then, right? So we're mapping these residue classes, now just represented as integers, because residue classes behave like integers in many ways. They add, they multiply, right? They don't divide, or anything. It's not defined. Anyway, so we're mapping 0, 1, 2 of Z3 into 0, 1 of Z2. Okay? Now, the previous theorem, we just showed that for a homomorphism and an isomorphism, that the unit of your G maps to the unit of your H, right? Now, what is the unit? Yes, that's a group, that's a group, that's a group, that's a group. So therefore, it has a unit. What is the unit? Well, it's this one, right? The zeros. So those are the two units. Therefore, under F, this one will map to that one, right? So we know that immediately. That's a theorem, right? The unit maps to the unit. So 0 mod 3 will map to 0 mod 2, right? Okay. So what about this one? What does this map to? What is 1 in Z3? 1 in Z3. Yeah. What does it map to? Now we only have two choices, right? This one here, it maps either, there are two cases, either into 0 or it maps into 1. Okay, so two cases. So let's systematically talk about those. So let's take the first case, that 1 in Z3, this one, maps into 0. Okay, so we have two choices. So it maps to 0 or it maps to 1. Okay, let's say it maps to 0, right? Now, so f of 2, we're using integer notation, the shorthand. And if you want to translate that back, what are we talking about? Well, this 2 here would be this, right? Because we're mapping something, we're mapping some element from Z3 into some element of Z2. Right? So f of 2, now just by the rules of residue classes, I'll write them out here. So right, that's why I say residue classes behave like integers, because you've got this kind of thing. All right. So that could be 2. 1 plus 1, so that would be 1, 1. Right. So f of 2 is 1, 1. This is just this. Okay. Now we're assuming f is homomorphic, right? So this splits to this. Okay. Now we've assumed that 1, this one here is this one is that maps to 0, right? So if 1 maps to 0, so you get 0 plus 0 is 0, okay? So that means f2 equals 0, maps to 0. Right? f2 maps to 0. We assumed f1 maps to 0, and we know that 0 maps to 0. So 0 maps to 0, 1 maps to 0, and 2 maps to 0. So that all three members of this are now mapping to 0. So by definition, that mapping is a trivial homomorphism. Okay? Because they all, it's like this, they're all mapping to the 0, which is the unit of this one. Right? This E here would be the unit of Z2, which is 0, which is this one. Strictly speaking, it's that one. Right? That's the unit of Z2. That's the unit of Z3. All right. now let's do the second case, where this one, the 1 here, maps to 1. Right? The 1 maps to 1. Okay, so here's the longhand way, here's the shorthand way, so 1 maps to 1. So residue class 1 mod 3 maps to residue class 1 mod 2, or in shorthand, 1 to 1. Right? 1 maps to 1. Okay, so just the same, yeah, what we're doing here is just the same as we did here, right? So, for the same reasons. Okay, so f2 is equal to f of 1 plus 1, which expands to f1 plus f1. That's because we're assuming f is homomorphic, right? So we can do that. Now we're assuming f1 is 1, right? So 1 plus 1, there it is. Now these ones here, what are they? They are, this one here is this, right? So 1 plus 1 would be like this, right? 1 plus 1 would be 1 plus 1, which is 2, but this is on the right hand side. This is in Z2. This is a result in Z2. Now 2 mod 2 is 0. Okay? So 1 plus 1 is 2, which is 0 in mod 2. Okay? So in other words, f of 2 is 0. Right? So if f of 1 goes to 1, f of 2 goes to 0. Right? But that creates problems, because look at this. 0 in mod 3, the 0 here, by using this again, is the same as 1 plus 2, right? Which is 3. 3 mod 3 is 0. Right? So using this kind of thing again, just the usual rules of residue class arithmetic, if you like. So okay, so 2 plus 1, that's 3, mod 3 is 0, so 0 is this, and we're assuming again f is homomorphic, so that becomes f of 2 plus f of 1. F of 2 we just showed was naught, okay, so put a naught here, and f of 1